I've never heard that before.
So, hi everyone. I'm Ahmed. I'm standing in for Prashant. I'm his postdoc. So, I hope I do not bore you to death today, because the topic is the very nice topic of distributed file systems. So, we'll start by having an overview of what file systems are in the Linux context. Then we will go through some issues in distributed file systems in general. And then we will describe today the network file system, the NFS. How many people do not know what an inode is? Okay, that's exactly what I wanted. How many people know but sort of remember what it is? Is there, okay. All right, so let us basically go through some of the basics of file systems in general. I mean, at the end of the day, is that from here? All right. Someone got a message. You have also last year's recording from Prashant, which is probably much better. So file systems is basically the abstraction that the operating system provides to you over the actual storage subsystem. So over basically whatever you have, well, if you have an SSD, if you have an HDD, if you have USB connected storage, like USB drive or something, all of these are basically abstracted using an operating system. And back to operating systems course basics, sort of what you studied years ago. An operating system is basically a virtualization platform, right? It virtualizes your hardware so that you can deal with your hardware in a more abstract, more simpler way. There are many file systems. So local file systems, and this is, for example, the reason if you have tried to install both Linux and Windows together. In Linux, you can read the Windows file system, but in Windows, you cannot read the Linux file system, right? If you have tried to have a dual boot machine, Linux can actually read almost pretty much any file system on Earth. Not any, but many of them. That's an exaggeration. But Windows, on the other hand, has like the network, its own file system, its own proprietary file system that it can deal with. So basically, a file system is the way that you abstract things, and file systems are in general, the abstraction for you as a user manifest as files and directories, right? So everybody knows what a file is and what a directory is. A file is basically some data that you have collected together that you give a name. The operating system, okay, has no way to interpret the sequence of bytes. So when you basically store a file, I can call a file ahmed.c, while what I have is this .key slice, right? Linux has no way to actually check if the file extension that I'm giving to the file, that I'm claiming that file to be in, is correct. What will happen is that when I open the file, okay, an application will try to interpret the file. So applications are the things that basically add the interpretation when you open a file. So if you saved it to a .pdf format, your PDF viewer expects some structure of your file. So it will have these headers on top, it will have these headers at the bottom, well, footers in the bottom, and you'll have some PDF specifics inside, right? So a file is a named collection of logically related data, and the operating system has no way to interpret it. It's the applications that do that. Some operating systems actually try to enforce such things as basically if you try to name a file in the wrong format, it will actually check if it's the right format, but this is a lot of complexity for the operating system to handle because there are just an infinite number of file formats now. So almost all modern operating systems do not even try to do that, right? The file system provides a logical view of data and storage function. It basically provides you with primitives to be able to open, close, store, retrieve, append, basically link, rename a file. So this is your file system abstraction, basically. It's a user-friendly interface. In many cases, you don't even know that you're using the file system, okay? And it provides basically the facility to create, modify, organize, and delete files, and provides sharing among users in a controlled manner. So to talk a bit about sharing among users, all files on Linux and even on Windows will have permissions, right? You can grant different users permissions, right? So I like John, I give him permission to my CV. I don't like anyone else, so I basically stop you from accessing my CV, right? So permissions, right? And it provides some form of protection because having these permissions, I basically know that if somebody messes my CV, it's John, right? So he's the person who I'm going to fight with, but none of you guys. So it provides some form of protection for you and your files, because not anyone can access all the files. So user files are basically a linear array of bytes, no records, and no file types. They're just like, to the operating system, it's just a linear array of bytes. It's just data that you store, you dump into your storage system. Directories are special files that are not directly writable by the user, meaning that in a directory, what you can do is that you ask the operating system to add something to a directory. A file system, the Linux file system in general, is you have the slash, okay? And then you have like etc, home, something, right? And in home, you can have multiple homes. So you can have Ahmed, Joan, I don't know, Nicholas. And then here, you can have things like, for example, desktop and whatever. And then you can have files. So you have some form of a DAG structure. It's not a tree, it's a DAG actually. And we'll talk about that very shortly, actually here. So a directory is basically a special file that stores this kind of data. And here's where the inodes are. The operating system does not understand English, right? I mean, computers do not speak English. They speak numbers. So an inode is basically a low-level representation of your file. So when you basically have a file that is called my CV here, okay? To the operating system, this means nothing. The operating system basically puts metadata regarding this file. And this metadata contains the inode number, which is a low-level number that the operating system can understand. Basically, it gives this number, this file, it's file number 5063, whatever, okay? And this is basically where your inode data is, okay? In a very abstract way. You have lots of other data related to the files, which will include the permissions, it will include when it was last accessed, it will include different things. And we'll go through some of these attributes, okay? There are other types of special files, which are like device files, or when you add device drivers to your system and so on. And these are basically, because everything in Linux is basically a file, which basically means that when you add a mouse, or you add a keyboard, or you add a new graphics card to Linux, it's just a file. So that's the way Linux actually communicates with the different devices. But we're not going through that now. The file structure is that you have directed acyclic graph, and that means that directories may not be shared, files may be shared. And by shared, we mean having links, right? Do people know what links are? Who does not remember what a link is? Cool. So, you basically have an inode number that represents a file, okay? And you have a one-to-one mapping to that inode number, okay? That is basically the file name. If you add a hard link, then what you're doing, and you do that using link my file, I can't remember, I think this is source and this is destination, I cannot remember now, to file 2. You basically, when you do a link, you're sort of adding an extra pointer to the inode number, which basically means that if you delete this, the file still exists because there is still linking to that file. Okay? So deleting a file in that case basically means that the file still exists because I have another link to it. This is what we call a hard link. You can have a soft link, which basically is a pointer to the pointer, which is sort of the shortcut in Windows. Shortcut to my file. Sort of. Okay? So this is basically linking. So in files, directories cannot have links. Why? Wild guess.
Maybe because they don't have like one inode. They're not files.
No, because what can happen if you have a link to the directory? The directories do have inode numbers, okay? So what can happen is that you end up with a cycle in the graph. So you basically have, you can end up with basically, if these were directories, right? And this directory is actually the parent of that directory. So suppose that here, because I'm just being dumb, I made a hard link that way. And I'm trying to traverse this tree. So I'm basically trying to find files everywhere in my system. So what would happen in that case if I have a link? So it will go down that way, and then when it comes here, okay, it's again, I mean, you can even have, I mean, of course, if you have even a third hard link somewhere, so you can end up with a loop in your system that is that will not be resolved basically. So for each file, you'll have a directory entry which contains the file name, the inode number, the major device number, which hard disk it runs on basically, minor device number if they're, these are details on what part of the hardware you're running on. And all inodes are stored at a special location on disk. It's called the super block.
Can we also not have directories with symbolic links that like that?
I think you cannot have, I don't know. It's worth trying. So we can try doing that. Not on John's computer, but when you go home, it's basically ln minus s, and then you put the two directory names. Okay? So all inodes are stored at a special location on disk. It's the super block, okay, which is the sort of a place in your storage system which contains like a map to your whole storage, right? What is stored where, okay? And inodes store 5 attributes and a multi-level index that has a list of disk block locations for the file. So again, a bit of review. So you have an inode table that basically has the different inodes, inode 1 for the different files, okay? And in each of these inodes, you reserve 12 bits basically, or 12 blocks to point to the different parts of the file. Because on the hard disk, on the storage system, you typically have the storage system divided into blocks. That's why they are called also block devices. Okay? A typical number for these blocks is 4 KBs. Okay? So you can have up to 12 4 KB blocks in a single file, which is very limited because that means that the maximum you can have of a file size is 12 multiplied by 4 KBs, which is basically 48, right? And this is very limiting. I mean, nobody has 48 KB files now, right? So, I mean, that's like my name. Actually, in Unicode, that's probably close to my name. So what people have come up with is the idea of indirection. How many people remember what indirection was? Okay, good. So we have one of these 12 blocks, consisting of just a grid of block numbers. So 4 KBs, okay? And you have all of these pointing to different blocks. And there you have 1024 of these in the first level of indirection. So you end up basically, you can end up with data all over this place. Okay? If your file is even larger, then you can do basically third level indirection by making each one of these blocks point to yet another (1024) addresses. So all of a sudden you end up with 12 plus 1024 multiplied by 1024. Actually, this is 11. Yeah, it's not really so. Multiplied by 4 KBs, which is 4 gigabit bytes. Okay? Roughly. It's not exactly 4 gigabits. So, using this form of indirection, you can increase your file size to as much as you want. And this is basically this part, the multi-level index that has a list of disk block locations of the file. Okay, so this is your multi-level index. Okay? Having said that, you can actually have an extra level of indirection, but then this will be excessive. So most operating systems will actually stop at 3 levels, and then if you try to store a file that is larger than 4 gigabytes, it will actually tell you that the file is larger than what the file system supports. It's again file system implementation specific. Okay, this is one way of doing file systems. Okay. The IO structure has these following fields: the mode, the owner ID, the group ID, the directory of the file, the protection bits, lost access time, lost write time, lost inode time, size, which is the number of blocks that this file has, reference count, and then the addresses that basically gives you the indirection. Okay? So this is basically pretty much what we covered until now. Okay? So now all of this was basically talking about single file system where you have everything on a single machine, nice and easy, single hard disk, maybe 2, but that's about it, right? Things get a bit messy when you start talking about distributed file systems. Okay? And in a distributed file system, what you're actually trying to achieve is that you're trying to maybe have 10 servers, have all their storage be tied together to give you the abstraction of having a single storage system. So you can basically you can all of a sudden have this very huge array of storage that shows up in your system as if it was a single storage device. Okay? So a distributed file system provides some abstractions and basically it provides also an API, okay, for you to communicate between the different storage devices. Okay? And then you have a process that actually implements the file service. So you basically have something on top of your normal file system that gives you this service. Okay? So file services, distributed file systems have 2 main models of implementation. Okay? The first one is where you have a distributed file system where when a client tries to read a file remotely, it will basically do all the operations on the file on the remote server. Okay? So everything is done with RPC. And everybody here knows what an RPC is, right? So everything here is done through some remote procedure call, and the file stays here, all operations occur here, and so on. The other model is basically, you copy the file from the server to the client, okay? The client does whatever processing it needs on the file, reads it, modifies it, and so on, and then pushes back the updated file to the remote server. Okay, and these are two different ways to build a file a distributed file system. Each one of them has its own pros and cons, of course. Okay, so in this case, the server is stateful, right? Because you sort of need to make sure that you know who is accessing the file in parallel, because multiple people can be accessing the same file at the same time, right? You should have some semantics for consistency for the sharing, okay? On the negative side, now you have a single point of failure. You have a single performance bottleneck. Everybody, if that file becomes popular all of a sudden, well, that file is basically being read by 100 users, 1,000 users. It becomes quickly a performance bottleneck. Reading from that file or doing any operations with that. And also consistency becomes a nightmare, because if all 1,000 users are trying to write in parallel, that means that how do you actually manage consistency in that case? And there's a lot of communication involved, because every time you want to read, you basically have to send an RPC. Every time you want to write, you have to send an RPC. Okay? On the upload-download mode, what you have is that you have a stateless server. Okay, the server doesn't have to really care about what's happening on the client side, right? Because at the end of the day, the client will just push the changes. Now, if the changes if there is inconsistency between different clients pushing the changes, then this is the classical consistency problem. But then this is another thing, right? Now it's just managing the consistency rather than managing who's accessing what. So you push the file here. So it's a stateless server, which also means that it's very simple to implement. Basically, you upload the file, you read the whole file, change it, you push it. Okay? And on the other hand, you basically need to actually move the file from the remote storage to the local storage, which means that if you, for example, your file is pretty large, you don't have enough space, this can fail. Okay? Direct question? Oh, sure. So this is one issue with this model. Okay? Plus all the overhead that comes with consistency. But on the other hand, file read, the slowest thing on your single computer, on like this computer, is accessing disk, right? The slower than the slowest thing is actually trying to access storage data from the network, because you all of a sudden add the network delays plus the actual storage read and write delays, right? So it's in this case, it's very slow in the beginning to actually load the file, but once you have the file, everything goes pretty quickly. So if we have a stateless server versus a stateful server, in the stateless server, no information is kept at server between client requests. Okay, so you don't have any notion of who's doing what, and that means that every time a service is requested, the client has to send every single bit of data that is required to access the file, meaning that it needs to basically send. So what kind of info would you need there? You would need things such as every single time you need to send in your capabilities, your permissions basically. You need to send in what part of the file you're going to read, okay? Or what part of the file you're going to write to. Because it's stateless, the server knows nothing about where you lost picked off, or where you lost left off, right? It's basically, it has no notion of all of this. And every time you do that, the server will have to check if you have the permissions, right? So, because that's the way it is. But this is again, yet more tolerant to server crashes, because the server crash means that since the server did not store anything, the server does not need to restore anything, right? If you know nothing, and if I know nothing and you shoot me, right, and I get resurrected, I still know nothing. I mean, you don't need to re-inform me about anything, right? So it's the same thing. You have a server does know anything. You shoot that server, you bring it up again, and well, you lost nothing because you stored nothing. Okay. A stateful server, on the other hand, sorry. It maintains information about the client accesses. Every single thing that the client does, the server needs to store because it needs to know everything about every single client. And basically, it shortens the requested message, the number of messages requested, because you no longer have to basically every time send your permissions and where do you want to pick off and so on. It is kind of giving you a bit of better performance in terms of the amount of communication that you need with the server, in terms of what you actually can perform in this case, because right now you can do even more stuff since the server has a state. So in that sense, it is actually better. Here is where it gets really hard, because I don't know how to say that word. I then put in a C. Okay, being that word, having that property, okay, means that you will actually, if you repeat the same command twice, okay, it will only the effect will only happen once. So suppose that you're concatenating to the end of a word the letter A, okay, and one of your requests basically gets delayed, so you think that the request got dropped. You resend the request once more, okay, so now you have two commands to concatenate an A, right? And idemp, that system will basically concatenate A just once, right, not twice. And in this case, consistency is much easier to achieve. Saying all of that does not mean that stateful is better. Actually, NSF from the beginning was stateless. They basically relaxed this a bit. And that's for a reason, because basically a single failure means that you need to update your whole system. A network partition, you know what a network partition is? When basically some of your clients end up on a segment of the network, cannot connect to you, do stuff on their local replicas of the file, and then all of a sudden try to access the state server, the main server, and there's basically this inconsistency between the two views of the world, right? So stateful is not always better. So now to the NFS, to the file system architecture, and this is basically, so let me just say some identifiers here. NFS is pretty much based on what implementation you have. Okay, so there are many implementation details that might differ between different implementations. But on the other hand, there's some basics that will be present in any NFS system. Okay, this is how the architecture looks like. You basically have the client, okay? You have a system call layer, system calls coming from applications or users. You have a virtual file system, which is like your normal Linux virtual file system. You have basically two tracks. Either the data is on the local file system, and then you basically access it through the local file system interface, or the data is available remotely. And in that case, you actually go through the NFS client. The NFS client basically provides you with an interface that resembles the local file system interface. Okay? But what it actually does is that it fetches the data from remotely. To fetch the data from the remote server, it uses RPC. Okay, so you have an RPC client running over the network that communicates to another RPC client that goes through the NFS server, that goes through the virtual file system for the remote host, that goes back down to the local file system. So, in reality, this is your NFS. Everything else remains the same. Okay? So this is what you add to the system. NFS is not really an add-on to your operating system, for example. It's not like you're adding a kernel module to the operating system. It's more like an interface that enables you to do this kind of communication. Okay? There are multiple NFS operations. They almost entirely look like normal local file system operations. Okay? There are two major NFS versions that are still in use. Version 4, which is the newer and better one, which is actually stateful. Okay? And version 3, which was stateless, but still is being used because people have been using have that version installed since forever. Right? So I mean, people have just not upgraded their system. And you have, these are basically the operations that you will find even in a normal file system, like create, read, write, and so on. And you have some of them are actually supported in version 3, and some of them are supported in version 4 only, some of them are supported in both versions. And there is a reason. Since, as I just said, version 3 was stateless, that means that, I mean, lots of the system calls were not truly implemented the same way. They will get abstracted, as we'll see, but you didn't have any way to save state. And the two important syscalls is the open and close. Open and close is basically the way that you deal with Linux files. Everything in Linux you use open and close to deal with that, even the device drivers, right? Even when you're opening a device driver, when you're trying to talk to your graphics card, you're actually opening a file, right? So open and close are pretty much the center of normal file systems. But they were not implemented in version 3, okay? They were actually abstracted, as we'll just see. So, on the other hand, version 4, since it's stateful, okay, it actually implemented open and close because it could keep the state on the server side. Because the thing is that open and close, I mean, do you know what is the return type of open? If you call open in C or in, what do you get?
Integer.
Yeah, integer, file descriptor. Right? And that file descriptor is basically what you use to communicate with that file. So to have open implemented truly, you need the server to know that number, right? Otherwise, it doesn't make sense. I mean, that number is actually a pointer to that file, sort of. It's not a pointer because it's an int, but it, in reality, it basically tells the operating system what file you are trying to access. So you need some form of state to be in the system. So this is version 3 implementation of open, okay? This is version 4 implementation. And with some add-ons. So there is also a very famous syscall, which is lookup. Lookup is basically a call that enables you to check if that file even exists. So the way that version 3 would make you open a file, would allow you to open a file, it will just basically take the open call and instead do a lookup. Check if that file even exists. And if that file exists, okay, it will return a lookup name to the client. The client can then basically issue a read command, and since it's stateless, the client knows that, well, my server is stateless, right? It will basically send in all the headers, all the information that is required for this read to actually go through the file. Because all the state is kept at the client side. Okay? On the other hand, when you're using the version 4 NFS, you basically can sort of send a bunch of calls, of syscalls, of NFS calls together. So you do a lookup, an open, and a read. All of them at the same time. The server, since the server can actually store state, so it will do the lookup, find the file, because you need to find the file, okay? And then it will do the open, return the file descriptor, okay? And then do the read using the file descriptor that it actually got, and send data to the client. Can any one of you tell me why is the performance on the right-hand side better than the performance on the left-hand side?
There is only one column.
Exactly. Here you have 2 round trip times. So you have this time, this time, this time, and that time. So one round trip time, second round trip time. Here you have a single round trip time. Okay? So it's actually this is a performance optimization. Okay, any questions? Am I going? Yeah.
So this version 3 and 4 are they equivalent in the sense like they're useful in different cases, or
No.
is it a consideration that version 4 is better?
Version 4 is better. So
What's the reason for moving to a stateful architecture?
because basically, well, there is a long, pretty nice article on the Linux journal. It's called "Why NFS Sucks." Okay, it's from 2006. Everybody basically realized that, okay, I have this system that, yes, allows me to access data from the remote server, but it does not provide me with any consistency guarantees, right? Because, well, it was the case that even one of the famous issues with version 3 is that since you do not keep state, one process reads a file, okay? So it is now operating on some local cache of that file. The other process comes in and removes that file, right? So that file no longer exists on the server. So that process when returning, okay? I mean, that is basically a very weird state. And then it's left for implementation, of course, so everybody will implement his own solution. So should you basically rewrite that, whatever was, so which one is the correct one? Is it the one that removed it, or is it the one that has a copy and wants to write it? So I mean, it was very notorious. There are all of these guidelines basically telling you, you shouldn't really use an NFS server with your email client because, well, if you delete an email while another email arrives, you can end up with your mailbox basically in some limbo state. So people basically pretty much knew that NFS sucks. It was a very useful tool at a different time. I mean, we're talking about like times when computers were much slower than your phone, and they had less memory than your phone, basically. But now you can do much better. Okay. Also, network speeds have gone extraordinarily fast. So now you have like I don't know if there's something that's called, for example, RDMA, remote data memory, remote memory access, basically. And that is something from the 80s, right? And basically it hit the wall because it's basically you accessing remote memory on remote servers. So if you have 1,000 servers, you can basically build a larger memory by aggregating the memory. Sort of an NFS, but for memory. Nobody was using it, or it was used in very few applications because it was very slow. Networks were very slow. I mean, you had to dial up and stuff. But now networks are basically much faster and much cheaper. So you can do all sorts of like network of network connectivity quite fast, and which basically helps you keeping states and stuff. Okay. So what happens when you mount? Do you know what mounting is? Okay. Who doesn't know what mounting is? All right. So great. So since the way that we said that the file system basically starts from slash, right? And then you have like the normal etc, the different directories for Linux, whatever these directories are. Okay. Sometimes you basically come in and connect your USB your USB hard disk. Okay, and when you connect it, you want that storage that all of a sudden appeared in your system to go somewhere. Right? Where do I put it? Should it be in slash? So mounting is basically telling the operating system where should you put this extra storage. Okay? So you can have mount, and then you basically suppose that your connected device had 2 folders, and these 2 folders were desktop and documents. So mounting is basically telling the operating system, okay, take this bunch of storage that you just got and hook it up somewhere, mount it somewhere. So this is mounting. Okay? So what you want in an NFS system is to be able to mount the remote directory, right? You want to be able to mount the remote storage. So this is a server which basically has this folder, Steen, exposed using the NFS. Because you can have different parts of your storage exposed or not exposed in your system, right? In your NFS system. So you have this as what you allow people to actually access using the NFS. So basically mounting is basically taking this part of the file system and sort of hooking it up somewhere. Like here, you hooked it up in a VU, which is like Vrije Universiteit, which was where Martin works. And you take that part and hook it up here. Okay? So you have it mounted. Another person can mount it in a me folder, and then you have me, and then you have whatever was in Steam, which is Mbox. So this is how mounting works. And mounting does not mean that you have transferred the data, right? Mounting just means that you can read these files and these directories. So you can see, you can access that, although it is remote. Okay, so what you're copying is just metadata. It's not the full structure. Now it gets more interesting because, as we said, a network file system, you are trying to aggregate the storage of multiple servers, right? Which means that your server can be both a server and a client. So it has this, it can play 2 roles. In some roles, it can be mounting something from another server. In some roles, it can be basically allowing others to mount whatever it has. So there is nested mounting or crossing mounting points. Okay? Suppose that server A was acting as a client to server B, basically mounting this folder, that install folder, which has some installed binders. Okay? And it mounted it over here. And now, client wants to mount this whole blob of data into its file system. So how would basically NFS work in that case? Again, since version 3 did not have any state, it was stateless, they actually decided that for security reasons, if you mount this, we're not going to show you that. Right? I'm not going to keep state of anything. I'm not going to try to keep security state or try to check on it. No, you'll get basically an empty directory if you try to access this. NFS version 4, you can't, they basically said, okay, users are, but they actually know that this is a networked file system, which means that if you already allowed something to be mounted, you use permissions, because you can have permissions on per directory basis. And if that user have the correct permissions to access this, and since I keep state, I can actually tell the user, you know, you're permitted to access this or you're not permitted to access this, right? Because I'm keeping state now. So I keep state of what, of the permissions of this mounted folder. Okay, so now the client can do nested access, which is an interesting thing. Okay? Auto mounting, there's a command that's called AutoFS, auto file system, that you can use to basically tell, because the thing is that since there are multiple users typically on these machines, so NFS is used in supercomputers, it's used in data centers, it's used in such settings where you might have 1,000 users. And these 1,000 users, each one of them can have a home. Okay? So, and it might be the case that my home and Ben's home actually have some common data that we can share because we're in the same research group, right? So we share data together, right? So if Ben is mounting his home directory in some previous versions of NFS, it will actually just mount his home and my home. So it will mount everything. Everything, all the home directories. Okay? Anything that is exposed through the NFS will be mounted at the same time. On the other hand, auto mounting is sort of an optimization that allows you to mount what you only need. So, for example, when you log in, you mount your home. Once you log out, you get unmounted. Unless someone is trying to access that data and he has the permissions to access that data. In the book, you'll find also talks about how auto mounting has actually in some implementations hurt performance because auto mounting it became even an extra layer of abstraction and you have to go through auto mounting every single time you mount. You do any disk operations because you wanted to check is it mounted or not. So you went through auto mounting and then it might be mounted. Everything was directed through the auto mounting module. This has changed somehow, but as far as I know, that Prashant doesn't really go through this in his lecture. Okay, but it's in the book. So if you're very much excited about network file system, you can read more about auto mounting. There are file attributes. So since NFS is designed to be very flexible, meaning that it can handle multiple file systems at the same time. So it might be the case that the 10 servers that I have, each one of them runs a different local file system. So one of them runs NTFS, one of them runs extended second, one of them runs extended third, and so on. So to basically enable all these file systems, I mean, each of these file system implementation has its own attributes and its own things that are exposed. So to basically enable this portability, what they did is that they decided that this is the absolute mandatory file attributes that should be in any file system that is supported by NFS. And these are 4 attributes that sound pretty long, actually. The type of the file, is it regular file, is it a directory, or is it a link? Okay? Which is like every single file system should have what type of file it is. Is it a directory, is it a file? The second one is the size of the file, and there is no plausible implementation of file system that does not have the size as an attribute of the files. The change indicating to see if and or when the file has changed, basically allowing the user to see when was the last time that file changed, which is again almost in all file systems that exist on Earth, this is part of these file systems. And the server unique identifier of the file system. Basically, the file system itself should have unique identifier. So if it's extended 2 or extended 3 or whatever. So these are basically mandatory. Okay? Implementing NFS on other file systems like Windows. Windows is actually very notorious, right? I mean, running NFS on Windows is A, very hard, B, it almost never works. Okay? So I mean, but Windows has its own, like, shared network thing, and they use different protocols. They use, you can share directories in Windows. You can have on Windows other types of distributed file systems. They have their own things, right? But running the NFS protocol on top of it is very hard. This was basically what was required by version 3. Version 4 added an extra set of, well, we would really like the file system that we operate on to have these attributes, because then it allows us to give you a much better experience, because we are keeping state now. And if we're keeping state, we can do all sorts of magic for you. We can do consistency handling and all of these things. So, first of all, an access control list associated with the file. So if you're using NFS version 4, you want they would really like to have an access control list. Who can access this file? Because that's stuff that they can handle. The server provided file handle of this file, a file system unique identifier for this file. So you want the inode number, basically. You can even have locations in the network where the file system may be found. So the file system can expose itself to the network, basically saying that I'm in this subnet, for example, right? So location. And then the character string name of the file's owner. So if I own the file, Ahmed, then it should have like I own the file, right? Time when the file data was lost access, time when the file data was lost modified, and time when the file was created. Okay? And these are recommended. If not implemented, it will still work, but probably with some issues. So, a bit more on the consistency side. On a single processor, if you have two processes, and the process, and you have a file that had AB originally, and process A writes to this file the character C. Okay? Process B will never be able to access if that process has the file descriptor, has a handler in this file, it will lock the file. Sorry. So process A will lock the file and will write C, and process B, surely when it reads the file, it will read the most recent copy of the file. On the other hand, in the distributed file system, where you do not have state and no locking, you can have a file server that has AB. Client machine number 1 takes a copy of AB and writes C to that copy. Client machine number 2 reads that copy, okay, reads the old copy, while this one is still not updated. So you can end up with these kinds of things. And again, this is for stateless NFS. So there are multiple semantics for basically for enabling and for making sure that things are consistent. There are the Unix semantics, which is basically every operational file is instantly visible to all processes. Okay, which is, if you know how Linux actually works, then you have two commands. You have write, you have the write syscall, which actually buffers the write, and you have fsync, which actually forces the write. Okay, force synchronization. So unless you call fsync, you might end up with something that is more, somewhere in between the Unix semantics, which is every operation in the file is instantly visible to all processes. Okay? The second one is session semantics. Session semantics is basically, okay, I get the file, you get the file, and when I close my session, I'm just going to dump it. Okay? And there is a relaxed version of the session semantics, which basically says that my session is 5 seconds or 30 seconds. So every single change that I do in the past 5 to 30 seconds, depending on what I set as my session time, as my expiry time, will be written. So every 5 seconds, I go and write to the remote server. Okay? So this is session semantics. And if you're not using fsync in Linux, you're actually closer to the session semantics with a bit of tweaking. That's for people who actually remember what is the difference between write and fsync. Okay? You have immutable files where basically every single change you make to the file creates a new file. Okay? And that way, your file is not changed. And I think if you're going to cover HDFS, HDFS has this sort of like, it's like Git. Everybody has used Git, right? You can always go back to something in the past, to a past version of the file. Since the file is immutable, every change you do basically makes a new file. And when you add this new file to your server storage, okay, you have all the different versions of the file. Okay? So no updates are possible. It simplifies sharing and duplication. I don't know if you're going to cover HDFS or not, but if you are, then this is also some nice feature in HDFS. And then there are transactions, which is sort of your database, atomic. You know what atomic is, right? It either happens or it does not happen, nothing in between. So you either have the full write happening, or you roll back to state before the write occurred. And this is more like towards databases and stuff, because this is actually having atomicity is a very, very hard thing, right? You can always also break atomicity. Think of things that breaks atomicity if you're not doing it in hardware. Okay? So, NFS being a very nice protocol and its designers being very relaxed and very hip, they basically said that, you know what, implement whatever you want. Right? So it does not enforce anything. So you can have your own NFS implementation that decides that, you know what, I'm going to use Unix semantics. Especially in NFS version 4, where you can actually do that, because you have the states. Okay? But most implementations will go for the session semantics, which is that much easier. Basically, every 30 seconds, I'm going to push my changes. And you know, most files and file systems are actually write once, read many. I mean, most file systems. This is most file systems. Very few applications actually are more like never read and write many times. Version 4 again introduces, since all of a sudden we have state, so we can also have locking. I mean, if I can keep state as a server, then I can have a lock. And I can basically say that, you know what, this file is locked, you cannot touch it, right? And if you do that, then you can go to the Unix semantics. It's actually, lock actually creates a lock for a range of bytes, so even a large file, a 4 gig file, you're not going to write to the whole 4 gigs at once, right? You're going to take a chunk, 2 megabytes or something, write to it, and this is what you're changing. So locking here creates a lock for a range of bytes, okay? And it is non-blocking, which basically means that you as a user, or you as the NFS implementer, okay, you should check for the locks. It's not going to block you. If two processes try to access the lock, they will both acquire the lock and you will end with a deadlock. Okay, it's non-blocking. If it's blocking, then it will stop one of them from accessing the lock. Okay? But since it's non-blocking, then the processes, both of them can access the lock. So what you need, the lock is more like for you a flag that basically tells you someone owns that, do not touch it.
If it doesn't block, then how is it a lock?
This is a non-blocking lock. This is a concept in distributed systems. There are many new systems that are implemented that way, where your lock. I'm not sure if I think these are just 4 kinds of locks in the system. There might be a blocking lock, I don't know. But the whole idea is that the lock is more of like a flag. It's atomic to acquire the lock, but you know, if you have 1,000 processes trying to access the same file at the same time, you do not want the server to actually be the one checking the logs all the time. You want them to retrieve that data and just check the log, and once the log is available, you can try to acquire it. But it's a systems thing, right? It's I know it sounds very weird, but it's more. You can test whether a conflicting log has been granted, so log T, okay? And you can basically remove the log from a range of bytes, okay? And you can renew the lease on a specific log, because in these distributed systems, there are actually many systems that now implement that distributed file systems. The idea is that you acquire a log for 50 milliseconds or 50 seconds or 1 minute or whatever, and then your lease expires. Okay, and then the other processes can basically access that data. So you can renew, you can ask to renew the lease. And yet again, this is implementation specific, because you can make it as strict as you want or as relaxed as you want. Okay? So this is like how locking would ideally behave. So if you're building your own NFS client, you want to make sure that if the current file denial state is none, okay, then anything you try to do, any operation that you try to do should go, read, write, or both. If you have a lock on the read, because you can't have only a read-only lock, right? If you might basically implement it such that all other reads fail, okay? I mean, this is more of as far as I understand, this is more of a suggested locking mechanism for your client implementation rather than what you really have to implement. Again, NFS version 4 allows you to do caching, which basically means that the client application can cache some data after reading it from the NFS server, okay? And this cache data stays in your memory, and then you flush it whenever you want, based on what we just said, which is basically you update every 30 seconds or something, okay? And again, this is the Sun implementation. Different implementations do caching differently. It's a very, very relaxed protocol. Of course, if you're having NFS installed, you're going to use one implementation. You're not going to use all of the implementations together. You also have delegation. If you remember in the beginning of the lecture, we talked about two models to access files. One of them was basically to copy the file and do all changes on the client and then push the file back. The other one was through RPC. Old style, old school NFV allowed only for RPC calls. Okay, so you would only go use RPC to read, to write, to do anything. Okay, and that's why you had basically to send all the information that you needed when you did the read and when you did the write and so on. Okay, everything was done at the server side. NFS version 4 allowed you to actually do upload download as part of the protocol, and that is using something that they call delegation, where the server basically delegates its responsibility to the client. Okay, and at any point in time, the server can decide that I'm revoking my delegation. So what would happen is that client asks for file, server sends the file with delegation. Okay, so now there's a local copy. Now the client can operate on this local copy for as long as it has the delegation. Okay, now suppose that a new client process comes from here and asks for the old file. Okay, now the server recalls delegation, basically telling the client, okay, no longer yours. Client pushes the new updated file, and the new process can now read the file, and they go back to basically normal RPC operation. Okay? And we are very close to being enough. I sleep, lots of people requiring more sleep. how do we make it, how do we make sure that duplicate requests do not basically mess up our system? So suppose that you send a request to append A to the end of the file. Now, old school NFS, sorry, there are just too many of these abbreviations in my life now. So old school NFS used to use UDP. Okay, UDP is like the internet protocol that provides absolutely no guarantees on anything, right? It's just like I'm throwing in a request, and then I don't even care if I get a response, sort of, right? And it basically leaves for the clients to do whatever they want with handling requests failing and so on. New NFV4 using well, it's RPC basically. It's because it's using RPC. RPC was using UDP. RPC now uses TCP also, so it's a bit different. But in general, you get this case when you basically you send the request and you're not really sure. You wait for some time and you're not really sure if it failed or if it's just delayed. So you send it once more. So the way that at the server these identical requests are handled is that each of these requests get an XID, a request ID. Okay? And when you resend the request, you resend it with the same XID, with the same request ID. Okay? And there's a cache here. And that cache basically checks if that request, or I've seen that request before, or if it's completely new one. So in this case, for example, both of them arrived. The server side knew that, well, this is the same XID. I'm doing the processing. I shouldn't do anything. Once the processing is done, I send the copy here and I cache the request here. Okay, in my cache, in my local cache. Suppose now that that you have that you have basically a client that sent request ID 1234 and waited for a long period of time. And while the server was sending the reply, the client basically became impatient and sent a new request. Okay? Again, same XID, right? Then what would happen is that this request will be completely ignored again. Now suppose that in reality that what you did is that you sent an XID, you got a reply, but your reply was shut down on its way. Basically something happened in the network and you lost that response. Okay? But when you did the calculations, what you actually do is that you kept something in your local cache. So when you get the same request with the same request ID, what you're going to do is that you're going to fetch the answer from the cache rather than try to go and redo the same request. So NFS old school did not have any security, which basically meant that you were sending your data on like the clear. There was no encryption. Well, there was no. If you do not have state, then how would you keep keys, right? You know that encryption requires keys and stuff, right? So, so since there was no state, there were no keys, and thus everything was sent on the network. If you know how to use Wireshark, if you do not, then you should. Because it's a really cool tool. So you run Wireshark in promiscuous mode, and you collect the data from the whole network that is unencrypted, and you could read all the data that was sent. It was okay if you were running on LAN on local area networks, but it doesn't work if you're running on the internet. So now you basically. This has evolved into having some sort of a secure channel. And to use that, it uses secure RPC. Secure RPC is secure remote procedure calls. It actually uses Diffie-Hellman, DES encryption. It provides you with lots of these things that you can use to actually encrypt your data. So it's just like HTTPS. When you're accessing web page through HTTPS, you don't really do anything, right? You just get the data, but it's encrypted. It's your browser that's communicating with the server in HTTPS. So it's quite similar. Secure RPC provides you with multiple ways to provide security. Most common is DES and Diffie-Hellman for key exchange. Okay? You know what DES is? It's an encryption. It's one of the most popular encryption protocols that got replaced by AES at the Advanced Encryption Standard. The first one I can't remember. It's DES was something encryption standard. Go ahead. Replica servers, NFS version 4 supports replication. Entire file systems must be replicated if you're doing multiple replicas because all of what we have talked about does not handle fault tolerance if the actual storage fails. Version 4 now supports some form of replication, and you use the FS_location attribute for each file to basically know which part of the network is it in. And replicated servers is again implementation specific. And thank you. Do you have any questions?
So
Okay.
you still need to build something on top of NFS, or can you use NFS?
You can use NFS out of the box. So what you do is that you get NFS in some form on some implementation. So you get, when you install, if you install Java on your on Linux, you can install the OpenJDK, the Oracle JDK, and so on. So you just pick an implementation and stick to it, right? So and the implementation, the system administrator will actually handle all of that. I think you guys are using EdLab, right? So EdLab is actually built on NFS, and you just get your home directories through NFS, right? Does anybody know that he's using NFS? I mean, to you, it's just hidden. So you pick an implementation. Once you have picked the implementation, then it's just implemented for you.
So you said that maybe there's no changes to the kernel. Like, does it need to be loaded, like the NFS?
Yes, you need to install it, of course. Yes.
Install it, so it will happen. It's not a user level thing, right? You'll be at the system level, OS level.
It's more on the OS level. It's more like it's intercepting your syscalls and making sure that they go the right direction, right? Because this is what is happening. But you don't need to recompile your kernel or to reinstall Linux to basically have NFS running.
About the mounting part, since you can mount a directory, and you can have nested mounting with mounted directory inside mounted directories. Doesn't that create cycles in your file structure?
So the question is, since mounting you can mount nested directories, would that create cycles or can that create cycles in your file system? I think you can, but you have to be like really, really working hard to get it to that extent. Because yes, you can. I mean, but it's I don't. Yeah, you can. So short answer, yes.
So doesn't that create some problems?
I mean, the NFS version 4 basically believes that, Linux allows you to do rm-rf / right? You can remove your root directory in Linux because they believe that you're capable enough of doing all sorts of things. And actually, I mean, that as dumb as that sounds, you'll find Quora question on what was the dumbest thing that you did in your internship. And there's a guy who went to Dropbox and did rm-rf / and he actually he pressed tab, but tab did not complete, and he pressed enter, and he was sudo. And he was working on their main branch. Yeah, and they do DevOps. Everybody now uses DevOps, so it took them a day to actually recover from that. I know someone who is running a whole data center, the Ericsson data center in Lund. It's a whole data center running actually backing applications and stuff. And at 11 at night, he decided that he wants to reinstall some machines, but instead of basically installing a subset of the machines, reinstalled everything like into blank. So I mean, you have all sorts of, it took them 10 days to actually recover that data. with calls from banks and from people basically pretty unhappy with their performance. So at some level, people trust that if you're using that, you kind of know what you're doing, right? Okay, thank you.